So I will provide a few recent results about the sea level rise in the 21st century. I will try to avoid overlaps, but I'm not entirely sure I managed to. So first, as a reminder, I will mostly address process-based methods to evaluate that. So here I remind the different components of sea level rise rapidly. I will focus on ocean processes because this is what is most easy to model in our climate models. I won't address small ice sheets and glaciers. Well, I can just say that the estimate of expected sea level rise for 2100 for these is something between 7 and 26 centimeters. Another talk, the next talk, will address the contribution of Greenland and Antarctic ice sheets through surface mass balance changes and dynamic processes. I will say a few words about land water storage changes, because I'm not sure this will be addressed in other talks and we have to be, in a way, comprehensive. And, of course, gravitational effects due to land ice and land water mass changes. This has been addressed already. So as a global climate modeler, actually I drive global coupled models, climate models. I see to some extent the future sea level rise changes as a byproduct of future climate change modeling. I will explain why it is so. So to try and explain how we model future sea level rise, I thought it was quite useful to remind the rationale behind climate modeling and how we actually integrate radiative imbalance in our models. So this is a naive picture of the greenhouse effect with the solar light coming in and outgoing long-wave radiation at the top of the atmosphere. So the imbalance is currently something like 1.6 watts per square meter for the entire planet. And actually, the new method to drive future climate simulations is the following. So we now use representative concentration pathways. So the philosophy is entirely different compared to the previous one. Actually now, in these scenarios, we have the radiative imbalance at the top of the atmosphere described previously, which is the entry point to these scenarios. This is completely different to previous methods from the SRES IPCC scenarios, where actually there were scenarios for future demography, economics, energy uses, agricultural practices, and so on. And from these, methane, carbon emissions were derived, and then concentrations, and then the radiative forcing of the whole system. Now it's the other way. Now we have these radiative concentration pathways scenarios that are imposed, and then it's up to other communities to write, if I can say so, the future behind that. What are the compatible emissions behind that, for example? So here there are several new scenarios, the RCPs, these new ones. And so we begin from something close to zero radiative forcing for pre-industrial times, so namely the 19th century, the 18th century and 19th century, and then it's gradually increasing. You can see the effect of volcanic eruptions here. So far it's estimated, partly, and then we have the scenarios. We have the most optimistic one, which is the RCP 3 peak and decline, or currently the RCP 2.6. I will show what it's like afterwards. As its name indicates, it peaks in terms of radiative forcing somewhere in the middle of the 21st century, and then declines. So this is very optimistic compared to the previous most optimistic scenario, the SRES B1, that increased until the late 21st century and then stabilized at a quite low level. Now we have also
the median ones are represented by RCP 4, 5, or 6. Well, this one is actually quite popular, so that will be the one I will be showing in the rest of my talk. And then we have the most pessimistic one, the RCP 8.5. So by the way, as you understood, the figure just represents the radiative forcing in 2100, so at the end of the 21st century. So 8.5, of course, is the most pessimistic one in these scenarios. So that's the way these scenarios are built. And then, so behind these scenarios, we have compatible emissions. So currently, we emit something like 10 billions of tons of carbon. And actually, so this is still increasing in the most pessimistic scenario, up to 30. But on the contrary, for the most optimistic, the decline occurs quite rapidly during the 21st century, something in 2020 or so, so very soon, and then it declines sharply. So this addressed a criticism for previous scenarios. According to these criticisms, the most optimistic one was too pessimistic. So actually, a really optimistic scenario was designed. Note that in the end of the 21st century, the compatible emissions are negative, meaning that actually it implies some degree of carbon dioxide pumping or greenhouse gases pumping out from the atmosphere, negative emissions. And so now that we have our scenarios, radiative scenarios for the future, we need models. So that's, well, an example of a typical global climate model, the one from CNRM-Météo France. And so this is important to remind that actually these models are based on the laws of physics. So here we have an atmospheric model. They integrate forcing, so they integrate greenhouse gases concentrations or emissions. Coupled to this atmosphere, we consider the surface, land surfaces. There is runoff, actually, that goes into the rivers. This is delivered into the ocean. Ocean with sea ice, and everything has got a resolution of about 1 degree or 100 kilometers horizontally, which is the median resolution of that kind of model, new generation models. And so using several of these scenarios, so again, the most optimistic RCP 2, 6, 4, 5 intermediate, and the most pessimistic one, for an array of different models. So we get these estimates from that study from Yin et al. So 13 centimeters, that's dynamic sea level changes, which actually includes steric effects, ocean expansion, but also to some extent surface melting from ice sheets and big glaciers for some models in the coupled system, and then 18 centimeters and 28. So these three figures, three estimates, are not very different from each other for 2100. And if I go a bit beyond the topic of my talk for 2300, it's much more, of course, and especially under a very strong forcing. So there is quite a big divergence between these scenarios. So the first message is that the considered scenario matters. And also, if you see the different curves for the optimistic, medium, and optimistic scenarios, you see that every curve represents a model. You see that there is an uncertainty that increases with time. So now a few words about how to interpret model uncertainty. So I added this to my talk because I thought there were overlaps a bit, especially this morning. So I wanted to talk about that because I think it's perhaps useful. Actually, the models will respond to greenhouse gases changes by radiative forcing change.
Then this radiative change, meaning radiative imbalance at the top of the atmosphere, will be translated into a climate response, meaning the temperature will increase or precipitation will change, and of course also ocean heat uptake, because oceans will get warmer. But these models, as you saw in my previous slide, respond in different ways. They have what we call different climate sensitivities, due mostly to different clouds parameterizations, but also to other processes like changes in surface albedo. For example, if the sea ice is melting, the surface is getting darker, and this has impacts on radiative forcings. Water vapor also in the atmosphere. And nonetheless, different ocean heat uptake efficiencies, the different models have got different ocean models have different abilities to capture heat. A way to measure that, which is quite simple actually, is that we run what we call 1% CO2 experiments. We start from pre-industrial CO2 concentration. So this is a pre-industrial simulation with constant greenhouse gases and forcings. And then in this model, we increase the CO2 concentration by 1% per year until we reach the doubling, which means in 70 years we've reached doubling. For our new model in Météo France, CNRM-5, and this is for the previous model in blue. So you see already there are differences between two models of the same institute, meaning already more variability, year-to-year variability, but also a different response at the level of doubling CO2. 1.6 Kelvin or Celsius for the previous model and 2.1 for the new model, meaning that the new model is more sensitive than the previous one. That's already a hint of uncertainty in our models. And now this is a study from Kulbrot and Gregory about more or less the same exercise, but performed for many CMIP5 models, so new generation of models. So here they plotted in blue the ocean heat uptake efficiency. So you see that they classified the models here in ascending order. You see there are very different heat uptake efficiencies. The climate feedback parameter here, the alpha, is an ocean heat uptake efficiency, is the link between the temperature, the transient climate response that I showed previously, the 1.6 and 2.1 degree, and the CO2 radiative forcing F here. So something that we see already, which is quite interesting, is that when actually the transient climate response here is represented by the different crosses. So you see that for increasing alpha plus kappa here, the red plus blue bar, actually you see that the transient climate response is decreasing. So this is a way to analyze the differences between models. Now more results about the 21st century, late 21st century. Here I plotted results only for the most pessimistic scenario, RCP 8.5. This is just for CNRM SIM 5.1, but this model can be seen as rather typical after all. You will see that in the next slide. So this is, all processes that a typical couple model can represent for the future. This is the sea surface height, or dynamic height, for change compared to the late 20th century, compared to just steric effect, meaning ocean expansion due to thermal and haline processes. You see that they are very similar. This was shown already by Benoit in terms of regional structures. So what we can see is that we have a decrease in sea surface height all around the Antarctic. There is an increase in the Atlantic, And well, actually, this is very similar. If I show then the difference between different scenarios. So again, these three scenarios. Something which is quite interesting. So RCP85 is the same as in my previous slide. You can see that the spatial pattern is actually quite similar. The more you increase the concentrations of greenhouse gases, of course, the more the signals are marked. So you see that there is it's more negative here in the 8.5 than in the 4.5, and also in the Antarctic. So it's nearly linear, actually. So the concept of climate sensitivity as a linear response of the climate system to the forcing is quite valid. So this is for a collection of CMIP5 models. So this time this is a mean of what I showed previously, again for the three scenarios. So you see that the same message holds also for quite a large ensembles of models, 34 CMIP5 models. But as shown this morning by Detlef, there is quite a discrepancy between all these models. If you look at the standard deviation of that multi-model ensemble, well, it's in some places, as you can see, it's nearly of the same order as the signal. So this is a film for a more dynamic view of these ocean processes. You have to look at this fast because this is time here. Time flies. And then you have the global mean of steric sea surface changes. So this is to show you several things, that there is... Oh, I thought this would be projected several times because it goes so fast. So I will come back again. You see that there is a lot of year-to-year variability, particularly in the El Niño region. So there can be La Niña cold phenomena or El Niño warm phenomena. You see this is quite dynamic. You see that the way to the signals, the mean signals I showed previously, well, is not that linear in time. And so, well, that's what we can see in a real climate simulation until 2200. Now a few words about land-water changes. This is one study, but there can be there are other ones which have different results. This study shows that in 2100, that signal due to land-water storage changes could be as big as nearly 8 centimeters compared to late 20th century conditions. And again, things are a bit complex because this can be seen as one contribution to sea level rise, but actually this contribution is the sum of several contributions. A first contribution is water impoundment which is, well, actually it's water stored in dams. In this study, they assume that there is an increase until the early 20th century, quite a big increase, and then it levels off somewhat. So that's the amount of water in ocean height equivalent trapped in the dams. And this does not increase too much. Then there are other processes like deforestation, for example, of swamp forests, rainforests. All the water that is held in the forests will eventually evaporate and then condensate and fall as rain in the oceans. So this is quite a small contribution, but that can be taken into account. Actually, it's up to 1 centimeter in the future. Oh no, that's something else. Deforestation is this one. There is also closed river basins. So there are quite big river basins in Asia, for example, where rivers don't
really go into the ocean, but this represents an amount of water that can change, and if it changes, it contributes to sea level changes. And there is that big contribution, which is partly due to water pumping, but also this process, it's groundwater depletion. That's the water that is in the soil that can be pumped, and again that will go to the ocean. Or other climate processes can be taken into account, like groundwater that is depleting due to drought, for example, in some regions, and all this will end up in the ocean again. So other studies assume that there will be more and more dams in the future, and since there will be more and more dams, actually more and more water will be stored on land due to that, and this will reduce the contribution of land water storage to sea level rise. So in other studies, instead of 8 centimeters, it's something like 1 centimeter or so. Uncertainties again. So a word on semi-empirical methods. This is clearly when such curves showing sea level changes in centimeters until 2100 are seen. Here, this is the previous IPCC assessment report. So between 18 and 59 centimeters sea level increase until 2100. With process-based approaches, so the approach I was showing up to now, so there is no reason not to talk about these semi-empirical methods. And which is interesting is that they produce generally a much bigger signal than process-based methods. It's radically different. So these methods rely on statistical relationships between past sea level and, for example, a predictor like air temperature. A common criticism that is addressed to these methods is that they hold for the past, but what about the future? Especially, it depends on what the learning period is. If the learning period is as short as 50 years in the 20th century, for example, it's due to the numerous non-linearities in the climate systems that form the future sea level rise. It's somewhat risky to extrapolate that for the future. If we are talking about longer periods, for example, a learning process about the previous millennia, for example, from paleoclimatic reconstruction of sea level, I would say this is also a bit risky because the changes that drove the recent past processes, these past processes are probably to a large extent very different from the processes that we are beginning to be faced with now with climate change. Instead of natural changes due to orbital parameter changes, for example, and some feedbacks, now we have an increase of greenhouse gases. This is the primary driving factor. And so we have to be quite careful, I would say. Another criticism is that most often sea level change is taken as a whole, and that its different contributors are not separated. And when we know that there are so many linearities in that, it can be a problem. But there are some studies where an effort was made. I think that's necessary to try and separate the different contributors. But personally, I would advocate for perhaps, if one wants to follow simple methods, I would advocate for something between this and the complex models. Perhaps use very simple models that can be very fruitful approaches, I think, and quite realistic to produce future changes. So this is nearly my conclusion. So again, that's Météo France's climate system as it is now, but we want to introduce new features. So actually, one of those, the ice sheets, in collaboration with LGG, so Catherine, next talk, I think, introduced an ice sheet model, which is quite difficult in a global climate system. Well, she will perhaps say why is it difficult and why these models are not a priori compatible with our climate models, but I think we were managing to do that these days. Another quite important issue is to try and put groundwater formulations in climate models. So that's what we are doing also right now. And so there are many other ways on which we can work. Also, the current system is at 1 degree resolution. So and the whole climate modeling community moves towards much higher resolutions, because clearly some processes are better modeled when the horizontal resolution is better. And thank you very much. This is the end of my talk.